Hi, hello, welcome back to VSM Math tutorial. So today we are going to discuss about Fourier transform concept, very important concept in engineering mathematics. So what exactly the Fourier transforms? If we already familiar with Fourier concepts like Fourier series, half-range Fourier series of standard periods like 0 to 2 pi and minus pi to pi, then harmonic analysis. So the continuation part of the Fourier series is nothing but Fourier transforms. We have so many other transforms also like complex transforms, Laplace transform, but Fourier transform is one of the interesting concepts. The basic prerequisite for this, as I told, Fourier series concept. So what exactly Fourier transform? So Fourier transform indicate or how to define this. The infinite Fourier transform. This Fourier transform is also called infinite Fourier transform, or it is simply called the Fourier transform. So this Fourier transform is defined for a real valued function. Okay. So Fourier transform of any real valued function f of x is defined by f of x. Here this capital F indicates Fourier transform operator. So f of x equal to integral minus infinity to plus infinity f of x e power I times ux into dx, provided this integral should exist. So since it is integration with limits, definitely we'll have some result after the integration. So that result, it is usually in terms of u. So that is the reason. So it is denoted by f cap of u. In some textbook, this will be written as capital F of u also. Both are correct. Okay. So Fourier transform of f of x is defined by minus infinity to plus infinity f of x e power iux dx. So provided the integral should exist, and the answer of this particular integral is in terms of u, and it is usually denoted by f cap of u or f of u. So the inverse Fourier transform. So this is Fourier transform. If we want to find out inverse Fourier transform of any real valued function, how to do that or how to find out that? So the inverse Fourier transform of f of u is denoted by f inverse of f of u or f inverse of f cap of u. This is small f and this is capital F. Both are same. So since some textbook will be referred as f cap of u and some textbook will refer as f of u, I have written both. So what this answer? So f inverse of f cap of u is nothing but 1 by 2 pi integral minus infinity to plus infinity f of u e power minus iux into du. Remember, when we are operating inverse Fourier transform, so the integration is with respect to u. So after simplification of this particular integral, we will get answer in terms of f of x. That means, so Fourier transform inverse or inverse Fourier transform for any function f of u is nothing but f of x. So these two are very important things in Fourier transform. That is the definition of Fourier transform and inverse Fourier transform definition. Okay. So based on this, we have some important basic properties of the Fourier transform. So we'll learn one by one. Okay. So the first important property I'll write. Before that I'll write. So properties of, what are the properties? We have some few properties. We'll discuss one by one. Properties of Fourier transform. Fourier transforms. Okay. So the first important property is usually called linearity property. Linearity property. So we know linear equation concept. Okay. So like that, linearity property is there in the Laplace transform also. Those who not studied Laplace transform, please concentrate properly. So first we'll write the statement of this. Very simple. What it states, if we have some constants like c1 comma c2 comma c3 dot 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 cn. If we have c1 c2 c3 c4 dot 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 cn are constants, okay, are constants. Then Fourier transform of C1 into F1 of x plus C2 into F2 of x plus C3 into F3 of x, etc. Cn into Fn of x. Cn into Fn of x. So what happens? So this answer should be C1 into Fourier transform of F1 of x plus C2 into Fourier transform of F2 of x plus dot 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 Cn into Fourier transform of Fn of x. So this is the first important property in inverse Fourier transform. Say we know how to operate Fourier transform for a real valued function. Suppose if we come across with any function which is multiplied with some constant. So how to operate then Fourier transform? It is simple. See, suppose if I consider this particular part, C1 is a constant, F1 fx is a some real value function. So what happens if I operate this Fourier transform, this C1 into F1 of x whole term, constant should be taken out, okay? So Fourier transform is applicable only for the function. That is the reason. So this should be equal to C1 into F of F1 of x plus C2 into F of F2 of x, etc. So how to prove this? Proof is also very simple. So I'll just prove this side once again. So inverse Fourier transform and Fourier transforms are very important. So as I told, the basic prerequisite for this subject is if we know a particular Fourier series concepts, then this Fourier transform is very easy. Okay. So I'll just erase this. It is taking some time. Proof usually nobody will ask in the exam, but one proof I'll do. Remaining properties we can check. So I'll do the proof for this here. Very simple proof for linearity property. So first we have to write the given data. What they have given? F of C1 into F1 of x plus C2 into F2 of x plus C3 into F3 of x, etc. Cn into Fn of x. Okay, so this is our left hand side. From this we have to prove right hand side. We know Fourier transform of any function. So what is that? We know that Fourier transform of any function, how to write? Integral minus infinity to plus infinity f of x e power iux dx. The same definition I'll apply for this whole equation. Let it be call it as whole equation. I'll apply for the whole equation. So what happens if I operate for whole equation? Integral minus infinity to plus infinity. So in place of f of x, we have this whole function. So I'll write whole function as it is c1 into f1 of x plus c2 into f2 of x dot 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 cn into fn of x into e power iux dx. Then we know in integration also, if any constants are there, we cannot integrate the constant. We will integrate only function. So what I'll do, I'll write that C1 outside minus infinity to plus infinity. So what we have? F1 of x e power iux into the x, because this e power iux is multiplied for whole terms, plus C2. I'll consider second term into this. So integral minus infinity to plus infinity f2 of x e power iu x dx dot dot dot. I'll write for the last term cn into minus infinity to plus infinity fn of x e power iu x dx. Now you just compare this term with this term. So what happens? C1. So it is like f1 of x e power I x dx. F of x e power I x dx is Fourier transform of f of x. It is the definition of Fourier transform. So instead of f we have f1. So what happens with this? So f of f1 of x plus c2 into f of f2 of x, etc. cn into f of, I'll write this capital F here, f of fn of x. So this is how we are going to prove linearity property, with respect to Fourier transform. So first very important property in Fourier transform, that is linearity property. Then I'll move on to the second important property in Fourier transform. Okay, so I'll just take that second important property. I'll erase this whole part. Each and every part I need to delete this. One second. So first time I am using this whiteboard concept, that is the reason little confusion and practice is needed. So what I'll do, I'll take eraser and I'll erase the whole part. Okay, it's very simple. Simply wasting the time by doing all these things. I'll take eraser and I'll erase it. So next we'll move on to second important property. So what is that property called? Change of scale property. This is very important. Change of scale property. Change of scale. Change of scale property. Change of scale property. What it says? Statement. So if we have, if Fourier transform of f of x, that is f of x equal to f cap of u, then Fourier transform of f of ax equal to 1 by a f cap of u by e. So this is change of scale property in Fourier transform. So proof, we have to prove this. Our proof is also very simple. So how to prove? As usual, we have to consider the definition first. So we know that Fourier transform of f of x. So what is Fourier transform of f of x? Integral minus infinity to plus infinity f of x e power iu x dx. Then in place of f of x, what we have? F of x. So that is, therefore Fourier transform of f of ax equal to, I'll just replace that minus infinity to plus infinity, f of x. F of x, what happens? It is f of ax e power iu x into dx. Now I have to simplify this because I need to get this result, right hand side result. So what I'll do, I'll take the substitution, integration method by substitution. What I'll do, I'll put this ax equal to some t. When I take x equal to t, then a becomes constant, x becomes dx, then t becomes dt. So a dx equal to dt. When we take the substitution, see, the main aim of the substitution is we are converting one variable into other, that is x in terms of t now. Since this limits are with respect to x, since I want to convert everything in terms of t, what I'll do, I have to change these limits also. Okay, so what happens? Let if x equal to minus infinity, lower limit is minus infinity. If I substitute here, what happens? T is also minus infinity because x is minus infinity. Minus infinity into something is minus infinity. So if I take x equal to plus infinity, t is also infinite, means infinity into something. So limit is varying from minus infinity to plus infinity only. So what happens if I substitute and simplify this? Minus infinity to plus infinity. So f of t, because ax is what? T. So f of t e power iux, x is replaced by what? This is ax equal to t or x equal to t by a, because our aim is to convert all x into t. So I need to remove this x also. So what happens? Because iu as it is, x should be replaced by t values. T values are nothing but t by a. X value is t by a into dx is there. Dx, what happens here? A dx equal to dt means dx equal to dt by a. That I have to write dt by a. So if I substitute all the simplification values here, and now if I simplify this, what happens? We'll check. This 1 by a, I'll take it outside. Integral minus infinity to plus infinity f of t as it is. Then e power I, as usual, since t is variable, I have to write what is the remaining term? U by a into t into dt. I just rewritten this term, okay, for my convenience to get the definition of the Fourier transform. So now you just compare this term with this term. F of x, f of t, e power I x t. In place of u, what we have? U by a. So dx with only variables. Therefore, based on the this one, I mean equation 1, I can easily write, so this as 1 by a into f cap of u by a. Okay, so very simple. Therefore, Fourier transform of f of ax equal to 1 by a into f cap of u by a. So this is what we call it a change of scale property. Okay, so this also important in the solving the problems of Fourier transforms. Now we'll move on to third important property of the Fourier transform. So I'll just take this statement, then we'll prove that also. So all the properties are usually not asked in the exams. This is only for students, I'm telling. For knowledge purpose, you have to practice all these properties proof. But in the exam, usually you may not expect, but in some syllabus they will specifically mention. They'll specifically mention that you are supposed to use this proof. Then in that case, if they're asking you to prove that, then you have to prove proof also. Okay. Let me go with the next important property, that is called shifting property. Next property is what we call it as shifting property. Shifting property. So what it says, statement, I'll write statement. So what it says, if Fourier transform of f of x equal to f cap of u or f of u, then Fourier transform of f of x minus a equal to what? E power iua into f cap of u. This is what the shifting property statement. A Fourier transform of f of x equal to f cap of u, then f of x minus a equal to e power iua f cap of u. So this we have to prove. So how to prove? As usual, simple. The base is for all the proofs is definition of Fourier transform. So we know that Fourier transform of f of x. What is Fourier transform of f of x? Minus infinity to plus infinity f of x e power iux into dx. You call this equation as 1. Then in place of f of x, what we have? F of x minus a. Therefore, Fourier transform of f of x minus a, what happens? It is equals to minus infinity to plus infinity f of x minus a e power iux into dx. Now again I have to simplify this by substitution method. Because I need to prove right hand side, I cannot keep this right hand side as it is. I wanted to get this. How to get this? Based on the definition of Fourier transform only. Means we need to convert this right hand side into the standard form of this Fourier transform. So here the extra term is x minus a. This has to be eliminated. So how to eliminate? Let x minus a equal to what? T. Then what happens? Dx equal to, because x becomes dx, a becomes 0, t becomes dt. So limit also, when you take x equal to minus infinity, t is also infinity. When you take x equal to plus infinity, t is also plus infinity. Because when you take x equal to minus infinity minus something, it is minus infinity, t is minus infinity. To take x equal to plus infinity here, infinity minus something, again infinity, so t is also plus infinity. Therefore, if I rewrite Fourier transform of f of x minus a, that is equals to, so what happens? So integral minus infinity to plus infinity, f of x minus a is there, so x minus a will be t. X minus a, what happens? Because x minus a we have taken as t, into e power I times u as it is, this x I'll rewrite from this. So x, what happens? T plus a, x equal to t plus a, you replace here, that is t plus a into dx. Dx is what? Dt. Dx is what? Dt. So if I simplify, so this you can expand the powers. Okay, e power iut into e power iua, because we know the rule. E power a into e power b is what? E power a plus b. So e power iut into e power iua, that we have to write. Since we are integrating with respect to t, that e power iua becomes constant, so I'll take it outside. Okay, if you want, I'll write that also. Minus infinity to plus infinity f of t e power iut into e power iua into d. Now here this e power iua I'll write outside. Remaining minus infinity to plus infinity f of t e power iut into dt. Now you can see it is nothing but f cap of u only, because it is nothing but Fourier transform definition. Therefore iua f cap of what? U. See, this term only I have, only variable change. When variable change, answer may not change. For example, x square between the limit 2 to 3 also same, y square between the limit 2 to 3 also same. Okay, so because we have limits, variable is different, answer should be same. Therefore Fourier transform of f of x minus a is nothing but iua f cap of u. So this is what we call it as shifting property. Shifting property. So very important property in Fourier transform. So the last one property is there, that is called modulation property. I'll give the statement, I'll leave the proof for your practice. So you have to do that proof by your own. As usual, simple, you have to operate definition, then you have to write the proof. So fourth one, that is called modulation property. Modulation property. Okay. So what it says statement, I'll just write statement. What it says, if Fourier transform of f of x equal to f cap of u, then Fourier transform of f of x into cos ax equals to 1 by 2 f cap of u plus a plus f cap of u minus a. So don't be afraid by looking at this part. It is simple only. Okay, when you are integrating, operating everything, you will get the steps. When you are looking first time, it looks, oh, it is something different. No, it is not different. It is as usual only. The only thing, when you are operating this cos ax in the integration, you have to convert that cos x in terms of exponential. Cos x outright in terms of exponential, e power iax plus e power minus iax by 2. This you substitute in the normal formula of Fourier transform, simplify, you will get the answer. Okay. So I think it's enough for today's class. I hope you all enjoyed this session and you like this session. Okay. So in the next class, we'll solve some more problems on Fourier properties. Today's class properties over. In the next class, we'll solve problems on Fourier transform. In the next class, I'll quickly revise once again all the formula, then I'll start the problems. Okay. So until then, thank you all.